Hi, welcome to the Signal Path. In this episode I've got another repair video for you guys, and this monstrosity that you see before you is the Anritsu 37347A. This is a 40 MHz to 20 GHz vector network analyzer, and it's unfortunately not functional, but this thing is absolutely enormous. It weighs a ton, and but you can see that it is otherwise, at least in fairly reasonable shape. It actually has an LCD screen. This is not a CRT, and it has its two ports, of course, here and here, and it supports an external bypass. In the front it has built-in bias Ts and so on, so it's a pretty capable unit. It must be at least 20 years old or so. I haven't looked carefully. It runs some proprietary operating system. We'll take a look at that, but yeah, there's something wrong with it and it doesn't work, and of course we're going to turn it on and see what's wrong with it, and hopefully we can fix it. I mean, this is not something that I would like to have in my lab per se, because it's just enormous and there's not enough room for it here, not at the moment at least. But yeah, anyhow, it should be pretty interesting to fix. I can see that push is already started to take a look at it at the back. But yeah, let's go ahead, turn it on, and see what happens. Alright, I've gone ahead and actually take the front and the back panel off the instrument, but I'm going to show you exactly what's inside later. I took it off because it's really heavy and difficult to move around, so I wanted to just have everything set up. Now the LCD screen on this unit actually does work. It's just really dim. I believe that the backlight, the tube in there has aged so much that of course it's not bright enough anymore and it has to be changed. We can worry about that later, but it indeed does work. So I connected it to an external monitor with a VGA port at the back, and let's give it a go and see what happens. So the hard drive inside the unit, it doesn't sound great, but there you go. You can see it actually booting up. It's saying attempting to download the firmware from the hard drive. Great. And there it is. It's reading records. Here we go. It's some, like I said, some proprietary operating system. I have to take a closer look, but the LCD does work. It's just really dim. Believe me, it's same thing that's being displayed on the VGA screen is being displayed there. And this is going to go on for a while. And I'm going to give you a break and we'll continue afterwards. Here we go. It downloaded everything inside, and it says initializing software, starting tasks, and so far so good. Definitely doing something. Come on, what are you waiting for? Oh, it's still trying to start these tasks. Aha, there it is. So that is what we're dealing with. Unable to set the date and time. I have to say that's a little bit disappointing that this instrument doesn't work because the date and the time cannot be set for whatever reason. Obviously this points out to perhaps a faulty BIOS issue with the memory or the backup battery or something in there that is preventing the date and the time to be set, and for whatever reason the software is written in such a way that if the date and the time are not set, that indeed it wouldn't start at all. So even if I wait here forever, it's just going to be stuck. Alright, and here's a look at the top of the unit actually, and you can see that most of the stuff is still covered. I have to take these two covers off, and this huge empty space that you see here, can you guess what that is? That's actually where the CRT used to be. The LCD is right over there, and right here at the very bottom is the LCD's backlight inverter, the driver. And this whole empty space, of course, was the CRT, because the CRT needs to be a fairly long structure with the electron gun and the deflector plates and all that, and the high voltage power supply. All of that must have resided in this area. But once they've switched onto an LCD screen model, they didn't change the chassis because they didn't want to re-engineer all the different mechanical things they have designed for the microwave components, which I assume most of them should be actually on the other side, because I don't see any of the couplers or bias Ts or anything like that. They must be all on the other side. And they didn't want to redesign all of that, so they of course kept the chassis exactly this way, and they just swapped it for an LCD screen, and the wire that connects the LCD screen, the ribbon cable actually runs directly under here and then goes down onto all the way back there. I have to reach out because I'm actually sitting quite far back in order to fit everything to the frame. This right here is the hard drive, which you might be able to see. Everything else is pretty self-explanatory at this point. Let's take a look up here before I remove the panels. And of course, as soon as we see this, a very recognizable shape, that's the gig oscillator. I'd imagine that it's a fairly broadband one. And this big heatsink here is likely has all the way down in there the drivers and the transistors that perhaps bias the coils in the gig oscillator. And you can see the output of the gig oscillator go into this structure, which is, I'm not sure exactly what it is yet, but perhaps a bank of filters and so on to handle the different frequencies of the gig oscillator and clean it up. I have to check. And then there's another unit over there, which I also still don't know what it is because I just opened it. Like I said, I haven't looked at it. And you know what? I'm just looking on the side. It says, there it is. It says it's a frequency down converter. Voila, there we go. Then we know exactly what that is. So everything else is hidden behind here and on the other side. So let's go ahead and take these panels off. All right, the screws are off. Let's see if I can get these guys. Oh boy. Here we go. Oh my goodness. So many cards. So many cards. It's kind of a little bit weird actually. It doesn't look like things are very well aligned in there. Oh, you know what I think it is? It looks like that's an interesting way to create a shield. I feel like these are all ground and they just have these shields that are held up by these pins. See, I'm actually straightening them up. See, there you go. That's weird, but anyhow, that's one way to do it, I guess. And there's this one down here. It actually has come all the way down. You can see I'm kind of fixing it up. There it is. So it looks kind of cool, you know. If this as a photo, like a wallpaper in the background of a PC, it looks kind of cool if I take a high resolution picture of that. And there it is. Here's a couple of boards. Here's the hard drive. So it's possible that this is one of these boards might be the board responsible for the operating system. Although I'm looking at these and these are kind of suspect now. Maybe this is the board because it also has two switches on it. Maybe a reset switch of some kind. Interesting. There's a whole bunch of LEDs on all of these things, which of course are status and so on, which hopefully are listed on the service manual and what they actually mean. All right, board number one. Here we go. Woo. Look at that. All through hole, of course. What else would you expect from an instrument this old? There's a 32 megahertz clock in the middle of this. This is definitely not the main processor board, but I'm going to hold it steady so you can go ahead and take a look at these components, and if you want to run them in Google and check out what they are, feel free to do so. I'm not going to dwell too much time on these boards until I find the one I'm looking for, because we can always come back and do some analysis and see if I can find a block diagram and go over the microwave components and sections, which are really the more interesting parts, because who knows what this board exactly does. I mean, there might be a description of these in the service manual too. Actually, you know what? There's something in here. There you go. It says this is the I/O interface number 1. It's actually labeled Wiltron before Wiltron was Anritsu. Interesting. Copyright 1994. Fantastic. There you go. So you can see this is some kind of an I/O board. Anyhow, this is not what we're looking for. So back it goes. Isn't it more fun not to read the service manual so we have no idea what we're looking at? That way we pull out every single board. There we go. Here's another one of those boards. Again, this is likely not the candidate. This one doesn't actually seem to have. Maybe it does. Let me see if I can see what it says. Sorry, still upside down. It still says Voltron I/O interface number 2. Who would have guessed? Bunch more components, all through hole. Nothing fancy. Some programmable components perhaps, because they do have some version and revision numbers on them. Another 20 megahertz clock up there. Bunch of 74,000 logic. And another clock down here. So some more I/O interface stuff, of course. Components only on one side. This is actually entirely copper core at the back. Complete ground plane on this side. But yeah, otherwise looks good. Now, you know what? I'm going to give up on these. I don't think any of these is actually the board we're looking for. I'm going to go directly to this one that I thought would be what our suspect board. So let's go ahead and take that one out. Alright, here we go. Took this guy out. This was actually quite difficult to remove. I'm not that impressed with the quality of these connectors at the back here that help you push in and pull out the boards. Maybe it's because they're very old, but they seem very fragile and they don't align very well in this mainframe. Here we go. Let's see what's going on here. There it is. That's our main board. There we go. I should have taken this out from the very beginning, from the look of it. A lot of really custom ICs on this. Obviously, this is completely a mystery to me. This actually is a Motorola, so this is probably the main processor. We should be able to look it up. It's a Motorola 68000. Fantastic. There you go. This is our main processor. And something else over here, which I don't immediately recognize, but I think it's also a Motorola, and it's made in Japan. There's a couple of other ICs, and check it out. Lithium battery. Here's our battery. So there it is, and this might be some kind of a BIOS there. Not sure what this is, but whatever it is, it's not fully populated. Perhaps some expansion of some kind. There's multiple ports here that were connected to nothing. Some more memory over here, and whatever these switches are, I don't know yet, but we will figure it out. But this is a good start. This is another thing. There we go. That's also important. Check it out. This also has, oh, look at that, timekeeper RAM. Oh, you know what? I do recognize this. If I'm not mistaken, this component actually has a real-time clock built into it, as well as a lithium battery. So this points out, I think this is our best chance. I'm not so sure if this is that important, but this is important because this has a built-in real-time clock. I've seen this before somewhere, I can't remember where right now. This is made by ST. So it has an SRAM, a backup battery, and a real-time clock with the crystal and everything all built into the same package. Now if this is damaged, or if it's dead, that makes sense why the date and time could not be set, if this is indeed what is holding the date and time. But this is our most promising thing. I hope there's a replacement I can find, because these are not repairable if they're dead. But anyhow, this lithium battery is likely also damaged, so I can go ahead and look for replacements for these. I am sorry that I'm hopefully not shaking this too much, but it's difficult to film all of this at once. But yeah, let's go ahead and dig out the data sheet for this and figure out exactly what it does. Alright, it's actually been about 2 weeks since I recorded the last section of the video you just watched, and in the meanwhile I went ahead and I looked up this part, and just as I suspected, this is indeed a component that has SRAM, backup battery, and a real-time clock and a whole bunch of other stuff on it. Now the interesting thing about this is that it's basically just an SRAM array, except for the fact that the real-time clock can be accessed through a specific address space of the SRAM. So by writing to that address space, you can set the time and the date of the real-time clock, and then it will maintain that because it has a lithium cell battery built into it. So lithium cell battery has some voltage sense and switching circuitry to ensure the proper regulation of the battery voltage, and that of course is bypassed if there is external power available, which then provides everything that's needed to run not just the real-time clock, but also the SRAM. But you can see there's a 32,768 Hertz crystal, which if you divide by 32,768, which is a very easy division ratio to accomplish in logic, you will get the 1 Hertz signal that you're looking for. And then there's also all the other necessary circuitry to run the clock and the oscillator and so on, and that way you can read and write to it and find the date and time. So this is a very good candidate of what could have gone wrong, and you can see this is a unit that I took out, and I went on eBay and I found in China a replacement part for it. Brilliant. It's basically exactly the same part, but you can see once it focuses out that it's exactly indeed the same. It's just that the text on this package doesn't quite is not quite white, it's gray. That's why it doesn't show up on camera very well. But this is the structure of that. Nowadays, of course, you don't make these type of things with package with a lithium cell on it. There's other ways to do it, but you know, it's a perfectly it was a perfectly good technology when it was initially available, when flash memories and so on wasn't so easily accessible, or maybe it wasn't even available at the time. I don't remember when flash was first invented. I have to look it up. But anyhow, so now that we know what exactly this is, and we have a replacement, which of course I have no way of knowing if it works for sure because the lithium battery inside it could have died, but I would be surprised if the lithium cell battery is the only problem this thing has, because it should still at least power on. It may not be able to retain the memory, but if there's power available, it should be able to work. But anyhow, regardless of all of that, let's go put it down into the unit, turn it on, see what happens. Alright, here we go, let's give it a try. I put the real-time clock that I just bought back in here. I left the lithium battery in because I really don't think that makes a difference, but I did take it out and check it, and indeed it is completely dead. But anyhow, I don't think that matters, just to hold the short-term functions and settings and so on, and I don't think that matters. So let's go ahead and try and see what happens. It's very difficult to get everything in one shot. This thing is enormous. I'm not sure why did you have to make this the size of the minivan. I'm gonna go ahead and... oh boy, here we go. Let's see now what happens. So far it sounds the same. Here we go. Oh yeah, I forgot, this thing takes forever to boot. So let's see if it starts doing what it used to do. There you go, it's loading the record again. I won't waste your time. We'll be back when this finishes. here we go. Now it's finished that, so it says initializing software again. And we used to do that before too. Starting tasks. Yeah, oh, what the heck happened? There it is, check it out! Aha, there you go, it boots. It's kind of silly to think that it wasn't booting because of that real-time clock. But anyhow, there you go, it's doing some self-test. It says self-test passed. Wow, this thing is loud. Look at that! That is nice. Now let's see, calibrating IF. Let's see what else is going to happen here. Oop. Here we go. So far so good. Oh, warming up. I had forgotten about this. Yes, I remember when I was using one of these old machines. Yeah, it has to warm up before everything stabilizes. This actually takes quite some time. So again, I'm gonna pause the video and come back. This thing has been warming up for 10 minutes now almost. Maybe time is going really slowly because I'm looking at it. But anyhow, let's take this opportunity while this thing warms up to talk a little bit about what's on the screen. Of course, this is a network analyzer, and this is a very typical Anritsu screen from the old network analyzers. They always look like this in the default startup mode, where they showed the S11 and the S22 directly on the Smith chart, and they broke the S12 and the S21 into magnitude and phase, which is very useful as a starting point. Of course, right now the instrument is uncalibrated, but you can see that it's set to sweep from 40 megahertz to 20 gigahertz, which is a full span in 401 points. And you can also put it into CW mode, which would be very useful if you want to use it as a synthesizer. For example, if you want to monitor a particular S parameter as a function of time. So again, I've used network analyzers all the time, all the way from starting these crappy old ones to the latest PNAXs and so on from Agilent, from Keysight I should say. So, but this thing is taking forever to warm up. It's been going on for some time, but while it's warming up, I did notice a couple of things which is actually of concern. If you look carefully here, you can see a couple of red LEDs that are lit. Now those LED LEDs, if you happen to look, you probably can't see from where you're looking, but this is an unlocked signal. Means that some synthesizer is not locked, and there's multiple of these. There's one here, there's one here, and there's one there. So they're up. You know what? Just as I was saying, speaking of the devil, check it out. Before it even told me, I already knew that something is wrong. There, error 6030. PHS is obviously phase, LCK is obviously locked, so phase like fail. BCDE, I'd imagine that's some kind of an error code that we'd have to look in the service manual to find out, but definitely confirms the LEDs. The phase lock of the system is unlocked. The PLLs are unlocked. There are multiple of them. As you can see, there are multiple boards. So there is something else wrong with it besides that clock, not real-time clock not working. So it's going to be quite a bit more challenging to fix this problem than it was to replace the real-time clock IC. But it's a good challenge. Even if you can't fix it, it should be very interesting to try and reverse engineer and debug this. Now, while I was warming up, I did take a look. There is a service manual. There is no schematic, but there is a block diagram, and there is some troubleshooting sequences and so on that I didn't bother to read. Maybe it'll be a little bit more interesting for us to just take a look at the block diagram and see what we can figure out ourselves. And you know, as I get stuck, most likely I will try and look at the service manual if I need it. Otherwise, it's kind of an interesting thing to try and just figure it out on your own. Well, believe it or not, it's been more than 6 months since I looked at this network analyzer. So I went back, looked at the videos to remember what I was doing because I had completely forgotten, and I believe we were just about to look at the architecture of the network analyzer to figure out why the phase lock doesn't work. Now, even though this block diagram looks really complicated, this is actually a very simple network analyzer. All modern network analyzers, including Anritsu's own modern units, as well as, for example, the Keysight PNAX, are far more complex because they can measure large signal parameters, X parameters, they can measure compression, conversion gain, noise figure, and a whole bunch of other features, which of course this is missing. A PNAX has more than 7 full synthesizers. This really has only one main one with sub PLLs built into it. So where do we start? Well, I want to explain this to you, but I don't want to also go into too much detail. So I'm gonna do my best to give you a general idea and then dive into the sections which might be more important. So as with any network analyzer like this, there is one main Yig oscillator that's going to be responsible for generating all the main tone that is not only the internal PLL but also the signal that's sent out of the network analyzer, and then the reflected signal and the through signal are processed in order to compute the S parameters. And that particular YIG oscillator in this unit is sitting right over here, and you can see that it can go from 2 to 20 gigahertz. So let's follow this signal and see where it goes. So the output of the YIG then will go through this amplifier low pass filter, and it will go through this pin diode attenuator, and this pin diode is used for amplitude leveling. You can see there is a control signal that comes from somewhere else, and I will talk about that, and this is what levels the amplitude of the YIG oscillator. And that signal will then continue, and depending on the frequency range that you're running the instrument at, let's say you're running it at the very highest frequency, it will directly go through, and if you're operating at the lower frequencies, it will then go through multiple low pass filters. Now, since the YIG can only go down to 2 gigahertz, there is a separate path that it can take in case you want to generate signals below 2 gigahertz. In that case, it will mix with a 6.3 gigahertz FFO, so it will sit at a slightly higher frequency, and that will then mix with this in order to create the frequencies which are lower than 2 gigahertz. So let's forget about that path for now, but remember that this path also has another oscillator in it, but this oscillator is free running, it's not locked to anything, so we don't have to worry about it. Either way, we can always pass it through this path and bypass this if this was an issue, but it doesn't lock anyway, so this is not the only issue. So we go through here, let's say we're at the high frequency, so we go right completely through. There is another low pass filter, and then there is another module here which is optional. If your network analyzer can go above 20 gigahertz, it has a doubler in order to take it all the way to 40. We don't have that, so forget about that. So it doubles and does a bandpass filtering. So forget about that, we don't have that. So we go through here, and then we amplify again, and then we enter the main transfer switch, and this transfer switch is what is switching the network analyzer between reverse and forward path, and that's how you can measure S11, S21, S12, and S22 by jumping back and forth between forward and reverse paths on the two ports that come out. So let's say we are on the regular path and we go through over here. We have a power splitter here, and this is really important because this power splitter is what generates the signal that goes through the main coupler and the signal that goes through the reference which is required for the S parameter measurement also. So one side of it will go through right over here, and check it out, ends up at port 1. So indeed the signal from the YIG does end up at port 1, and it should. And from the other side it also ends up on port 2. And that's how we have our main port 1 and port 2 signals being generated from our main YIG oscillator. Now at the same time, let me change color over here. At the same time, the other path goes through a level detector, and this level detector is what ultimately controls the ALC to do leveling. Remember, this leveling is required because we want to be able to control how much power comes out of port 1 and port 2 during S parameter measurement. That's really important, and that's what this portion is. Now this doesn't have a problem in our unit, because if it did, we would get amplitude on level, which we do not. And this then becomes our main reference signal, and that's really important. As I said, you need a reference signal in order to be able to do the computation for S parameters. So we have the two reference signals for port A and B, and we have the reflected signals for port A and B. And here are the four signals that you need in order to do S parameters. Now these four signals are still sitting at the frequency of the YIG. So if your YIG is, let's say, doing 10 gigahertz, you're going to be receiving a 10 gigahertz signal here. So this is the very first time where the signal is going to get converted to a lower frequency, and it's going to be done by these four samplers. And you can see the output of the samplers are sitting at 89 megahertz. How is that possible? Well, there's a comb generator here, and that comb generator is driven by a power amplifier. Now if you go back and watch a video that I did on a on a frequency counter repair, I talked about a step recovery diode followed by samplers which can down convert very high frequencies down to bands of low frequencies. And this is exactly what this system is. You have a power amplifier driving a step recovery diode which then drives four samplers, and that brings the frequency of the YIG down to 89 megahertz. So we've come down, and this 89 megahertz is not constant, which means that the frequency that is driving the comb generator has to be dynamic. And in fact, check it out. There it is dynamic, and there is a whole new PLL here. So let's mark that with a different color. Here's our first PLL that is built in, that is required, and it creates the signal necessary to convert down to 89 megahertz. So which means that this is actually in the path of our main PLL loop. So we have one PLL inside that loop already. Alright, let's continue on. So now these signals then go once again, then all of them reach yet another mixer, and this mixer then mixes them down all the way to 2.5 megahertz. So we have yet another portion of the circuit which has to have another PLL in order to generate a signal which then mixes down with the 89 megahertz and brings it down to 2.5 megahertz. And that one is all of this guy over here. So we have yet another PLL which then generates this signal. And take a look, the signal from the PLL on the left here is 357 to 536.6 megahertz, which then goes through the comb generator, and that's why there's a power amplifier, by the way. And the other one goes from 25 megahertz to 272.5 megahertz, and that is generated with two internal PLLs. So there's yet another PLL over here and another PLL over here, and the output of those two PLLs are actually mixed together in order to generate the 1 hertz resolution from a dynamic divider here. So anyway, let's not worry about that too much. So now we have one signal here, one signal here, and that brings us down to 2.5 megahertz, and you can see that that goes through over here, and it also goes through, if I can find where I'm going, over here, and one more over here, and that's 3 of them. Perfect, that's everything we need. So now if you look again, there is another mixer here, another mixer here, another mixer here, and that finally brings the signal down to 80 kilohertz. Now we are within the IF bandwidth of the instrument, but that requires yet another PLL, and that PLL is over here, and that would give us the signal necessary to connect to these 3 mixers, which then bring it down to 80 kilohertz. Now there is a bunch of calibration signals and so on are also generated internally, and that's how the instrument can self-calibrate in order to make sure that it has the right frequency centering and so on. So having said that, I'm running out of breath here. Having said that, the 380 kilohertz signals, which are derived from all of these, they actually, let me just connect them here for the sake of completeness. There we go. These 380 kilohertz signals are now sampled by synchronous samplers over here, which are driven from the 10 megahertz signal with an IF sync signal, and that will generate 6 DC signals. After all of this, these 6 DC signals contain all of the real and imaginary values required to compute full 2-port S parameters. They go through sample and holds, and there's an analog to digital converter which sweeps these one at a time and measures them all. That's why the sample and holds are there. And finally from that we can compute through this so-called quiet bus, which is just a digital bus. It can finally compute the 4 S parameters that are required to get the signal that you're looking for. So the S parameters are computed through this path. So where does the YIG get locked? Well, that is also fairly easy to follow. So the YIG goes through here, goes over here, it gets down converted, and look at that, there is source lock signal here, which is derived from the output of this mixer, and that source lock signal is then taken over here, goes through this other phase frequency detector, and then it goes through here, and then finally goes through here and locks the YIG. So the YIG is locked through this path, but this path needs this to be locked and this to be locked, but not this one, because this one generates the 80 kilohertz signal. We are looking at the signal before these mixers, so we don't need the output of these, which means that if our YIG oscillator is not locked, either this is broken, this is broken, that's broken, that's broken, or this broken, or the comb generator, or any of the mixers that are required to bring the signal down. So there is a lot that can go wrong here. Now having said that, pay attention to the fact that all of these signals are actually locked to the same 10 megahertz. You see 10 megahertz here, same 10 megahertz here, 10 megahertz here. Where is the other 10 megahertz? Here's the other 10 megahertz. Here's the main crystal of the unit. Here's the 10 megahertz. And you can see that all of the PLLs use the same main 10 megahertz of the instrument. So now, because these are each their own units, we can actually look at these signals individually and find out which of them is not locked. Now, I've been playing with the instrument a little bit, and the initial phase lock problem I actually accidentally almost resolved, and I'll tell you how I resolved that. Now this is a very subtle point. The Yig oscillator has a fine tune and a coarse tune. The fine tune is done by the FM driver, and you can see that it has a slope of -6 MHz per volt, and that is what's controlled by the main PLL loop. But there's also a coarse control, and that coarse control is let me change the color here. That coarse control is actually driven by this A to D converter, by this D2A converter and a coil driver. Now this D2A and the coil driver have a digital word that comes onto it, which then tells the Yig oscillator to roughly where to go depending on the desired operation. But let's say that you want to lock it at let's say you want to lock it at 10 GHz. This will put it very close to 10 GHz, let's say at 10.1 GHz. And then once it's at 10.1 GHz, the FM driver in a closed loop system will then lock it perfectly to 10 GHz. In my unit, because the battery had run out and the memory was flushed, the calibration file for this D2A converter was lost. But it was stored on the hard drive, and I actually restored it, and that caused it to come back to being roughly in the right frequency. So now it locks, but not all the time. There is still a minor problem where it occasionally seems to lose lock, and there is some problems, jittery problems with the signal coming out. So having gone through all of this, I hope you're still here. I would love to hear if you actually listen to this entire block diagram description. I'm going to now go back to the instrument, and we're going to identify some of these blocks, and I'm going to show you the problem. It may not be a serious problem, but it's still worthwhile investigating. So let's go back to the unit. And here's the shot I'm sure you've been waiting for to see. This is now looking on the other side of the instrument. Remember that the front of the unit had the Yig oscillator, which is right actually behind this. This is the floppy drive here. So on the other side of this, the Yig oscillator, the first down converter for the low frequencies, as well as the main filter bank was located. So we've seen it already, so remember that that stuff's over there, and all the other microwave components are here. We can easily follow them. So this is port number 1 over here, and this is port number 2 over there. And you can see that here's the coupler for port A, here's the coupler for port B, here's the step attenuator for one of them, step attenuator for the other one, here's the bias D for the first port, here's the bias D for the other port, here's the main transfer switch that switches the order in which the signal goes in and out and selects between the reference as well as the reflected power. Here's the main power amplifier, which drives the step recovery diode and the down converter mixer, which is all located in this block. Behind it is the main mixer for the main portion of the IF. You can see that the test signal for port B, the reference signal for port B, test for port A, and reference for port A are all handled in this little microwave unit here. So the signal that comes into the power amplifier for the step recovery diode is coming from one of the synthesizers. So this is one of the signals of interest to take a look at. There is also another signal which then enters this block at the top, and that's the one that drives the second banks of mixers, which brings the signal down to 2.5 MHz. So that's the other one that's of interest to look at. Obviously, all of those signals are going to come from the boards that we saw on the other side of this main motherboard, and that's where everything is handled. And there's Pooch checking everything out there. So you can see that all the boards that are over there are going to be our main synthesizers and PLLs, and those signals are fed over here. And the IF signals, once they're generated down to IF frequencies, where then you go through the A to D conversion, as I explained, go back onto those boards. And everything else is really pretty straightforward. There's nothing surprising here. The power supply is right over here, the main big fan is over there, but the signal path, no pun intended, is all clear. So the very first thing to do is to look at the signal coming out of the instrument, so I can actually show you what the problem with the phase lock loop actually looks like. And then we have multiple points in here which we can monitor to find out which of the PLLs is causing that little instability in the signal, which I'm not even 100% convinced might be an issue, but I think it shouldn't be doing that. Anyway, let's go and take a look at it and we'll find out. And we have 3 points of interest in here to take a look at afterwards. Here we go, everything is turned on and you can see that the error is gone. And right now I have port 1 connected to the input of my Keysight EXA signal analyzer, so we can take a look at the signal coming out, and look, it's measuring the 4-port S parameters and it doesn't give me any errors anymore after I fix the Yig oscillator lookup table. And you can see that, remember, this network analyzer right now is not calibrated, so I haven't done S parameter calibration, so these measurements are very crude. But you can already see that the S11 is all gathered near the center point here, which is 50 ohms, which makes sense because the input of the spectrum analyzer is 50 ohms, and S22 is open, so it's all rotating around the output outside of the Smith chart there, and the S21, S12 are obviously at minus infinity in theory. So it's working, at least it looks like it's correct. It's not generating any errors or anything like that. But let me show you the signal. Now, in order for us to see the signal, it's going to be very difficult as it's sweeping. So I'm going to put it into CW mode. First thing I'm going to do is I'm going to stop it from switching back and forth between the different forward and reverse path. You can see the light going back and forth, so it's going forward and reverse path. That's how it's measuring all the S parameters. So let's go ahead and change that. I'm going to change that so that we only measure a single channel. So now it's only measuring S11, and you can see that it's, you know, it's close to 50 ohms without calibration. And I'm going to also change that to CW mode. And let's look at something around, right now it's doing 40 megahertz. So you can see at 40 megahertz, it's right in the center here. So let's look at 4 gigahertz. So we are somewhere within the band of the gigahertz. Are nice in the beginning of it. There is our signal. You can see it's right there, and it's indeed, it cannot do exactly 4 gigahertz because it has limited frequency steps. Right now it's at 3.9821. So we can go a bit closer over here and take a look at the signal. You can see the 4 gigahertz signal is indeed coming out. So let's zoom into here and see if there are any issues. So here's our signal, and at first glance it looks okay, sitting at 3.982 gigahertz, which is what the instrument does because of its finite steps. And if I go ahead and change the span and look at the signal closer, you can immediately see the problem. So there is indeed something going on. This PLL is continuously coming in and out of lock. Now, it may be that this is normal and the instrument has some internal steps that it's going through, and in between, when the PLL isn't completely locked, it doesn't care anyway, because the unit is not generating any errors. You can see it's perfectly happy with generating the 4 gigahertz signal right there, and you know, it doesn't give me any problems. So I'm not 100% sure if that's an issue, but it could be. So nonetheless, even if it's not a 100% issue, it would be cool to try and trace it and find out which of the PLLs is coming from, because if we can detect it, then we really understand how the instrument works, and that itself is quite rewarding. So as I mentioned, a couple of different places to look for various signals. There's a couple of signals that different PLL signals going to different places. Obviously the easiest one to look for is the one that goes through the power amplifier. Now, in order for me to detect a lock, what I'm going to do is I'm going to leave the instrument in the same CW mode as it is, and I'm going to disconnect it. I'm going to connect it to a frequency counter, which can tell us how stable that frequency is a little bit easier than it is on the spectrum analyzer sometimes. So we can look at it on the frequency counter and see how stable that signal actually is. First thing, let's measure the internal 10 megahertz crystal of this unit just to make sure it's nice and stable, and that is easy to do. I'm going to use my HP 53131A, which is a frequency counter that I upgraded in the previous video with the 3 megahertz expansion over there. We're going to use that and go ahead and try and measure the 10 megahertz reference. That's pretty easy. So let me go ahead and plug this guy in, which is all the way at the back over here. There you go. That takes care of that. And not too bad. Check it out. We're looking at 10 megahertz and then 2 hertz off or so, which is not too bad. And that is very, very stable. You can see that it's not really moving around. Only the smallest digit is jumping around a little bit, which is totally normal. So I'm not worried about that. That means that we can move on. So the next thing we can take a look at is the signal coming from our first PLL. This first synthesizer going into the power amplifier, which drives the step recovery diode. Let's take a look and see how stable that frequency is. That's also part of the loop. And we can do that by disconnecting it and connecting it to the frequency meter over there. I have to cycle the power because I don't want to disconnect this and have it floating for some time before I can connect it. So let's go ahead and do that. Alright, here we go. We're nicely connected once again. The instrument is set to CW mode at 4 gigahertz. So now I am measuring the frequency of the first synthesizer, and check it out. 508 megahertz. Very, very nice and stable. Is not moving around at all. So that's indeed not a problem. So our first synthesizer, which I showed you, which had about a 500 megahertz range, and that makes sense also, has no issues. It's very stable. So we can eliminate that as an unknown. Now the second synthesizer is the one that down converts from the 80 something megahertz down to 2.5 meg. But if the frequency of the unit is set to below, I can't remember exactly how much it was, below 200 megahertz or so, then the step recovery is actually disabled and it will directly go through, which means that if the unit is set to 40 megahertz, I expect the second synthesizer to be at 42.5 megahertz. So we can measure that exactly. So this is the next thing I'm going to do. Disconnect that, connect it back to this, measure the frequency one more time, and see if that makes sense. And once again, now we're connected to the other synthesizer. The instrument is set to 40 megahertz. And you wouldn't believe it. There it is. I found a problem. Check it out. It's supposed to be set to 42.5, exactly what I said based on the block diagram. But check it out. It's not very stable. And that's exactly what we see on the spectrum analyzer when we see the frequency jump around. It's coming from the second synthesizer. So we've nailed it down. It's not a problem with the EEG oscillator. It's not a problem with the 10 meg reference with the first PLL. The second PLL is messing up. Unfortunately, the second PLL is also the most complicated PLL. It's the one that has an internal mixer and so on. So again, as I said, I'm not 100% sure if this is even an issue. For all I know, this could even be either dithering or it just simply be jumping between the points. Although I'm not fully convinced. But anyway, we can nonetheless go ahead and remove that board and take a look at it just to see what it looks like, even if we don't fix it. So before I try and fix that board, I'm going to try to do a calibration of the unit and actually measure something. But before that, let's flip it to the other side, take the board out so we can see and at least take a look at the PCB. And our second synthesizer board is board A2, which we can go ahead and unplug. I actually unplugged it and then accidentally erased that video, so I'm doing this a second time. And let's go ahead and take that out. And I've gone ahead and taken the shields out of it as well, so that we can take, oops, a closer look at it. So let's see what's on this board. Now if you forgot what the block diagram looks like, make sure you go back in the video and take a look at the block diagram, because it's really hard to get everything here in frame. So I'll just quickly explain what's going on here again. So if you remember that PLL had either a divide by 2, 4, 8 output or a straight through output. So here's our divider that can be programmed for different division ratios. Here's our selector switch, which then selects. So the output of this entire section, which are our 2 VCOs and our mixer, here's our first VCO, here's our second VCO, here's our mixer. The output of that goes through this divider and then selected via this selector here, and that jumps to this cable and then goes through here and goes back out of the back of the unit, and that was the signal I was measuring. So I was measuring the output of this from the other side of the network analyzer, and that's what was jittery. So somewhere along in this area probably is something that might be either dithering it on purpose, or that there's occasionally locks and locks back, unlock and lock mechanism, which sometimes happens to PLLs when they're not operating perfectly near where they like to be in the closed loop. So one of these components could be bad, but honestly, only if you guys are really interested in me going through the repair of this, I'll go back and do it. Otherwise, let's put this back together. It seems to be happy with the way it is right now. We can do an S parameter calibration and see if we can measure something, because that's really the real test to see if it works. But I know which card it is, I know which output it is, I know the exact symptom, and you figured all this out by going through the block diagram step by step and using some intuition on which signals to take a look at. And that's one of the messages I wanted to get across. So if you really want, we can go through the detail of this and find the problem by bringing the wires out. The problem is that obviously I cannot probe this while it is operating. It has to be inside the unit. And as soon as you put it in here, then you're running into the problem of, how do you access all this once it's inside? So you know how it is. And so as a result of that, only if you're really interested will I dig into it. So let's jump to the S parameter calibration. So I went ahead and I put the instrument to a 12-term regular standard calibration with my calibration kit over here, and it's a manual calibration routine. And you can see I'm also connecting it now to a bandpass filter, which is adjustable to measure its S parameters, and check it out, it works beautifully. The calibration was successful. I verified the calibration afterwards with some standard loads and it was good. So it looks like that there is no issue that I can detect, at least. Either the problem we were seeing is intentional for dithering, or that it doesn't really affect the performance because it's in between the measurement points. But so far it looks good. So let's take a look and see what we're looking at here. So I changed the display Type here to be just the magnitude of all the S parameters, so I'm not showing it on the Smith chart anymore, so it's a little bit easier to relate to on these plots. And here's S11, S22, S21, and S12. And right now the filter is set to 2.5 gigahertz. It's a bandpass filter, and you can clearly see from the S21 that we are letting the 2.5 gigahertz signal through, and we are attenuating it right outside of 2.5 gigahertz, but a little bit higher. And we have another mode where the signal leaks through once again. So outside of the frequency of interest, outside of what it is specified, it doesn't behave very nicely. But you can see that it is really well matched right at the frequency that it's supposed to operate. So right at the 2.5 gigahertz right now we have a nice deep notch in the S11, and S22 is symmetric, and of course the transmissions are also perfectly symmetric. I can go ahead and change the frequency. For example, I can increase it to 3 gigahertz, which is its upper frequency band, and you can see the S parameters shift with it. Quite nice. And right outside again we have this issue, which is undesired. And let's go back all the way to 1.5 gigahertz, and you can see here at 1.5 gigahertz it behaves quite nicely and behaves quite differently again. So it looks good. I should say I'm pretty happy with it. So whatever the problem is, again, it's not an issue or it's by design, but I would love to hear what you guys think. I think we covered a lot of material, the block diagram, really understand the instrument. It's very, very helpful. And if you guys like it, please let me know. These videos take a long time to produce, especially doing repairs and doing the reviews that I do. So let me know if you enjoy it. It's always nice to hear from you, and we can continue the discussion in the comment section.